Hello, this is Mr. White, and this video is on simplifying trigonometric expressions. And in order to be successful in this lesson, in this skill, you're going to need to be very solid in all the trig identities we've learned thus far. And as I've been stressing all along, I'm sure, you don't want to feel like you're memorizing these. These need to make perfect sense, and if they don't, please take the time to ask, because we're going to be using these for quite a while. You need to be totally comfortable with them. The reciprocal identities were basically just some definitions that we learned right at the beginning of our trig unit. The quotient identities, as discussed in the last video, is where with a good mental picture or a picture on paper of the unit circle, they should make perfect sense. Same with the Pythagorean identities. Those were born out of a picture and a good understanding of the unit circle. And the clue that you're going to use some of these. Let me go back to the first ones. What is the clue that you're going to use the reciprocal or quotient identities? Well, notice that all of those involve fractions. So if you see 1 over some trig function, or if you see a trig function over another trig function, that's a good clue that you're going to use a quotient identity or a reciprocal identity. For Pythagorean identities, anytime you see a trig function squared, you might use a Pythagorean identity. As we'll find in the, one of the examples today, it doesn't mean every single time we necessarily will, but you at least want to consider the use of a Pythagorean identity. Notice that every trig function is represented, and every one of them is being squared. Cofunction identity, that's one where I really stress you don't want to memorize that at all. That simply says that a trig function of an angle is equal to the cofunction of the complement, and that needs to have made sense. And the dead giveaway that you are going to use a cofunction identity is whenever you see 90 degrees minus theta, or pi over 2 minus theta, you're almost guaranteed to be using a cofunction identity there. And finally, the even-odd identities, which, one more time, a good understanding, a good mental picture of the unit circle makes very clear. Anytime you see a trig function of a negative angle, that's a good sign that you're probably going to use an even-odd identity. All right, so let's go to armed with those identities, let's go to our first example. Simplify the expression to a single trig term or constant. That means that our final answer is going to be either a single trig term, such as, let's say, could reduce to, this whole mess could reduce to sine of x, or it could reduce to cosecant to the third of x with the 2 in front. Those are both examples of single trig terms. Or it could just turn out to be a constant. It could just turn out to be 7. All right, so let's find out. All right, one thing that I often find when we get into this unit is that when I start throwing these identities at students, they often forget their algebra. Please don't forget your algebra. This is really about using trig identities, but don't forget your algebra. And in fact, I'd say that our first step here is an algebra step. Look at the top there and just go on a hunch and think, what do you think you could do algebraically with that? Well, I hope you're thinking FOIL. And notice that this is a difference of squares case where the outer and the inner terms of the FOIL will cancel each other out. So if I just FOIL as my first step, I will get secant squared of x minus 1. And the denominator, I'm just going to leave that alone in this first step and call it, and write sine squared of x. First step was algebra. Second step, what clues do you see there? Think of the, look over the list of the identities if you need to. What clues do you see there? Well, in both the numerator and the denominator, you see a trig function being squared. So Pythagorean identity needs to pop into your head. Now, question comes up. Should I use that on both the top and the bottom? Well, let's consider. If I consider the Pythagorean identity involving sine, let me look at the bottom first. If I consider the one involving sine, which most students find the easiest to grasp, I need to be comfortable rearranging this. And notice that I can rearrange that into sine squared. It says theta on the formula sheet there, but we'll call that x. Notice that that can easily be arranged as I've just shown there. And so that means that I could replace this denominator with 1 minus cosine squared of x. But that doesn't really seem like progress. Replacing a sine squared of x with a 1 minus cosine squared of x seems like a step backwards. It's not really simplifying it. So let's not do that. Let's ignore the Pythagorean identity for the bottom. But for the top, the secant squared of x minus 1, notice that that one gives us a little better luck. If I look at that corresponding Pythagorean identity, that one can be rearranged into secant squared, once again, of x minus 1 equals tangent squared of x. So again, you've got to be comfortable rearranging those, flipping them around. And so that's exactly what I'm going to do here. I'm going to replace the secant squared of x minus 1 in the problem with the tangent squared of x. And that will give me tangent squared of x over sine squared of x. All right, let me clear myself some space here. All right, next step. What clues do we have? We need to be comfortable rearranging this a little bit. Tangent squared of x over sine squared of x. We need to recognize that that's just tangent of x over sine of x quantity squared. Use your exponential rules, your algebraic knowledge to notice that exponent of 2 applies to both the tangent and the sine. So that is exactly the same as what we had in this previous step. And when you look at it that way, tangent over sine, what clue do we have? We've got a trig function over another trig function. That should make us think of our quotient identities. Now, the one that seems relevant here is the one that says tangent of x equals sine of x over cosine of x. And there are several ways we could try to implement this, but I'm going to just do the method that I think most students find most intuitive. And that is, once again, that's the quotient identity. That is to just replace this, this sine up here, this tangent, with a sine over cosine. Now, it gets a little bit uncomfortable because we're going to get fractions within fractions, but we'll be okay. So that tangent up top is really a sine over cosine, all divided by, and I like to make my fraction bar a little bigger there, sine of x. And that's all being squared, right? Okay, so if you're comfortable doing that, let's go on to the last step. Let's see if I can squeeze this in onto this screen. All right, that just takes some fraction manipulation. So when you have sine over cosine divided by sine of x, I'll invite you to think of that denominator as a fraction itself, if this helps. I find this does seem to assist a lot of students. If you think of this top as a fraction and the denominator as a fraction, you can use your fraction rules to say, oh, well, I take the numerator and I multiply it by the reciprocal of the bottom. So the reciprocal of sine x over 1 is 1 over sine x. And we see something wonderful happens. Don't forget the quantity squared. But when we do that, we see that a sine x up top cancels out a sine x down below. I end up with 1 over cosine of x, quantity squared. And our final step will be to say, let's use a reciprocal identity. 1 over cosine is the same as secant. And since it's squared, I'll write secant squared of x. And that is our simplified expression. I've written it as a single trig term in this case. All right? So if this felt a little foreign, if this felt a little uncomfortable, expect that it's going to take a little time getting used to applying your trig identities. But again, look for the rules here. Look for the clues, I guess I should say. Look for the clues that I mentioned before. All right. I want to make one more comment about example A. The book suggests, and I've often suggested in the past, that you check with a calculator. And while that is generally good advice, I will admit it's not totally practical all the time here. But I do want to say that if you're willing to, especially in a problem that's not quite as ugly as this, notice that I had to take this and in typing it into our calculator, I had to change a couple little things as should be familiar. Same with our simplified final answer. I had to enter it slightly differently into the calculator. But notice that if I do that, I'm expecting these two to be the same thing, right? So when I bring the graph onto the screen, not much really stands out at us, but what's probably going on is that that's probably our original function, our original expression, and the simplified one, if everything went right, should be exactly the same, right? Well, graphically, it's a little bit hard to tell if that's what's going on or not. So I find that using the table is most helpful. When I go to a table there and say, okay, this y1 represents the original expression, y2 is the simplified one, I notice there that, look at that, the y values are generally the same. The only thing that is different is that, as discussed in the last video, sometimes with identities, one side ends up undefined, and we just accept that and say, okay, it's still an identity. As long as when both sides are defined, we get the same result. Okay. Example 2. This one looks really ugly at first, but we're going to find it's not that bad if we look at the clues. I will mention that a good strategy to use sometimes is that at some point in the process, get everything in terms of sine and cosine. I'm not saying that's for every single problem, and I'm not saying you do it right from the beginning, but at some point in the process, write everything in terms of sine and cosine. So you'll see that come into play. But let's do the obvious thing first. There's a big glaring clue right there, right? That's just screaming for us to use our cofunction identity. So what's the cofunction of secant? Well, that would be cosecant. And the complement of 90 degrees, or pi over 2 minus x, is just x. All right, that's sitting right next to a sine squared of x. Up top, I also have cotangent. I'm just going to write out the rest of this, not get too fancy in this first step. But at this point, this is when I'm going to apply my own piece of advice. And let's write everything in terms of sines and cosines, using whatever identities are applicable. So if I want to get cotangent in terms of sine and cosine, I'll use the quotient identity. That's the one that said that cotangent is cosine over sine, right? It's sitting right next to cosine. I like to very deliberately write the cosine up high to make it clear that if I were to multiply that out, the cosines get multiplied together and the sine stays by itself in the denominator. So I invite you to do that as well. In fact, let me go ahead and extend that fraction bar. Why not? Same thing over here on the right-hand side, or the right-hand term. That's just a 1 over sine, right? So I've got a sine squared here. And if you can simplify this on the fly, that's cool. But I'm going to say cosecant using our reciprocal identity is 1 over sine. So that's times 1 over sine. And again, if you want to do put them over the same fraction bar, that's fine. Again, I repeat, you could cancel out the sign on the bottom with one of the signs up top. But you know what? I'm just going to let them hang for right now. On the bottom, I'm using a reciprocal identity. Once again, that's 1 over sine of x. And I could do that fraction thing where I say I'm going to take the entire top and multiply by the reciprocal of the bottom. You know what? I think that's actually is what I'm going to do. I was thinking of something else. You may see me in class sometimes try something different, but let's go ahead and do that. Let me do this the lazy way, just because I'm running out of room, really. Let me just take that and say I'm going to cross out that and just put sine of x over 1. And maybe I'm being a bad example because I really should be demonstrating how to show this clearly, but I'm going to be a rebel here. Okay, so I'm just doing a fraction operation. And the thing you got to remember is how to distribute this trig term. This is where I really need you to come and ask for help if you're struggling, because this is where I have a lot of students making mistakes. What do I distribute this sine of x to? Do I distribute it to this, 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 and this, or just something less? Well, I need to remind you there are really two terms between these parentheses that we really call this one term and this another term because they're separated by a plus sign. So we're going to distribute the sine of x to each of those terms. And look how convenient this just turned out to be. When I distribute the sine of x to that first term, that sign will cancel out that sign on the on the bottom. And that's going to leave us with cosine squared. So I'm going to give myself a little more room here. Let me extend the page here. So once again, the signs will cancel on. I'll end up with cosine squared of x. That was this cosine times this cosine, right? All right. How about when I distribute the sine of x to the second term here? Once again, it's going to cancel out a couple signs, and I'm going to end up with plus sine squared of x. And this is like the clouds parting in the sky and the sun shining through. Remember that this went away because we had flipped it and multiplied it up here. Well, this is really just over 1, and that is the Pythagorean identity, or that suggests the Pythagorean identity. Cosine squared plus sine squared is just 1. So guess what? That big, ugly, nasty expression that we started with, it doesn't matter what value of x you plug in, what angle x you plug in, it will always be equal to 1 as long as it's defined at all. So again, this is going to take a little getting used to, but here's your opportunity to practice. Pause the video at this point, please, and have at it. All right, let me put the answers up here. For that first one, you should have gotten 2 sine of x. For the second one, you should have just tangent of x. If you have any trouble with this, come on by.